Okay, so I next, in our tour of advances in quantum mechanics in the early 20th century, wanted to examine the Bohr model of the hydrogen atom. Now, recall the other day that we were saying that this is a semi-classical model, meaning that while it's not fully classical, it maintains enough of classical physics um, that it's going to have some flaws. So eventually we will replace the Bohr model with a fully quantum atom, but uh, it was a huge leap forwards, and um, so I'd be remiss if we didn't go over this. So Niels Bohr, 1913, uh, um, had worked in Rutherford's lab, recognized many positives about the Rutherford model, but also recognized some of the issues that we addressed the other day, um, that the electron is accelerated, and an accelerated charge classically should be radiating electromagnetic waves, which should be shedding energy, and consequently uh, should have the electron spiral into the nucleus and make it such that atoms aren't stable. So Niels Bohr is going to apply some of Planck's notions of quantization to the energy levels of the orbital of electrons. And the Bohr model will combine the Rutherford planetary model of the atom, uh, the Planck quantization, the photon concept of Einstein that we've discussed over the past couple days, and also Newtonian mechanics. And so, kind of um, our model that works either for the Rutherford atom or for uh, the lowest allowed state in the Bohr model, uh, the electron and proton in the hydrogen atom, right? The simplest atom, hydrogen, consists of an electron and a proton. I've written plus E here just because I'm only worried about the electric charge here. Um, Mass of the electron, some tangential speed v. So this Bohr theory basically uh, looks to this model and says that the electron moves in a circular orbit around the proton under the influence of the electric force. So instead of, you could think of this like Earth and Sun, instead of the gravitational force being uh, the force that we would say causes uh, this Earth orbit about Sun. Instead, you have this electric force which causes this orbit of the electron about the proton in our hydrogen atom. The Bohr model also uh, goes further by saying that there are only certain electron orbits that are actually stable, and Bohr referred to these as stationary states. He doesn't have an explanation as to why this is true, and in the coming lectures, um, we'll talk about some other really cool thought experiments um, to that end. But Bohr will tell you that uh, only some of the electron orbits are actually stable, and if the electron is in one of these stable states, it doesn't emit electromagnetic radiation. So since it's not emitting electromagnetic radiation, its total energy is fixed, and then we can apply Newtonian physics to describe the electron motion. What happens at other times? Well, if the electron transitions from a higher allowed state to a lower allowed state, then it has to give away energy as electromagnetic radiation as one of those Einstein photons, right? Such that the earlier energy minus the later energy, so this could be the higher state energy minus the lower state energy, is going to equal HF, which recall is the energy of a photon. Similarly, uh, in this Bohr model, we'll say that radiation, electromagnetic radiation, a photon, is absorbed um, by the atom if the electron transitions from a lower energy state to a higher energy state, um, such that uh, it needs to absorb an energy photon of exactly the right amount to carry it from the lower state to the higher state. So remember the other day we were talking about uh, the, the Kirchhoff uh, laws of absorption and emission spectra, and we were saying that the very same uh, uh, photons that are given off by a hot sparse gas are the very same photons that are absorbed if a continuous spectrum is passed through a cold sparse gas. Well, straight away, this Bohr model explains that. We also have this idea that uh, that Bohr is going to come to that says that the size of the allowed electron orbit is determined by imposing some constraint that the angular momentum of the electron about the nucleus is some integer multiple of h bar, where h bar is just Planck's constant h divided by 2 pi. In other words, I MEV ME times VR, which is the angular momentum of the electron in the circular orbit, is equal to nh bar, where n is some integer 1, 2, 3, etc. Well, we could look at the electric potential energy here. It's just going to go as K, the electric field constant 8.99 uh, uh, times 10 to the 9 Newton meters squared over Coulomb squared, uh, times the charge of uh, the nucleus times the charge of the electron divided by uh, the the radius of the orbit. And so in this case, um, since the charge of the proton, the charge of the electron in the hydrogen atom, there's one of each, but the charges are the same, just equal in magnitude, opposite in uh, one's plus, one's minus. The electric potential energy here is just minus K E squared over R. The total energy, as you've come to expect, is just the kinetic energy plus the potential energy. So that would be half the mass of the electron times V squared minus K E squared over R. Hooray! We also have Newton's second law that says that the sum of the forces is equal to the mass times the acceleration. And so here, the electric force, uh, K E squared over R squared, not R to the first in this case, right? Because we're talking about a force. K E squared over R squared is equal to the mass times the acceleration V squared over R. And that's mass of the electron, even though I've started to drop subscripts. We could solve this for kinetic energy, not this K. I recognize that I probably should have been a little more careful with my drawings, but the kinetic energy is half mv squared, and note that I have an mv squared here, so if I just divide this side by 2 and this side by 2, I have a half mv squared on the right, so I could say that half mv squared multiply r across is just k e squared over 2r, right? If I multiply r across, this r squared just becomes r. So half mv squared is k e squared over 2r. Well, now we have a statement for kinetic energy, half mv squared, and we already had a statement for the potential energy term. And so I could put this right here and get k e squared for 2r minus ke squared over r, we'll note that that means the total energy of the system is just minus ke squared over 2r. Perhaps from your Physics 130 days, you remember that this minus sign in the total energy just tells me that the electron is bound to the proton, right? It's a bound system. So the total energy being negative just tells me that the electron is bound to the proton. Hooray? Okay. So we also have this statement that was one of our postulates here, right? That mvr is equal to nh bar, and we also have this statement that the kinetic energy is ke squared over 2r, right? I can combine these two statements um, to I I and set them equal, right? I could solve for mv squared, or I could solve both for v. There's lots of ways of going through this, um, but here I've solved for v squared, right? Um, so ke squared over I over mr, solving this for v squared, right, is that guy. Solving this for v squared, I get n h bar over mr squared, right? So setting those guys equal, something cool is starting to happen. Note that we could solve for r, but what this does is it means that r is now related to n, and n is allowed to take on integer values, right? Since uh, n is only allowed to take on integer values, r is now related to uh, an integer squared times h bar squared over mke squared. And so this allows us to set the allowed radii of orbits in the hydrogen atom. In fact, when n equals 1, the ground state, we call that one the Bohr radius. And it is just when n is 1, so h bar squared over mke squared. If you plug that into your calculator, you'll see that it's about 0.053 nanometers, or half an angstrom roughly. Hooray! Um, if we wanted to know uh, another way of writing the radii of the electron in this Bohr hydrogen atom, it's just going to be n squared times the Bohr radius, right? Because here, all the stuff that isn't the n squared is our Bohr radius, and so r sub n is just n squared times the Bohr radius. Hooray! I would pause the video here and try and work from up here all the way back to this quantized radius. Once we've done that, though, note that we had that the total energy of the system depended on r, and since r is now quantized in this Bohr atom, so too is E. The total energy of the system, we could replace Rn with our solved value here, and we get that the total energy of the system is going to be minus E squared over 2Rn, which is also minus Ke squared over 2 Bohr radius times 1 over n squared, which, if you plug in what A naught is also minus mk squared e to the 4 over 2h bar squared times quantity 1 over n squared, where again n is allowed to be some integer, some positive integer. Hooray! For the hydrogen atom specifically, if you plug in the mass of the electron, k e to the 4 2h bar squared, you'll you'll get that the allowed energies are minus 13.606 electron volts over n squared. Again, n is allowed to be positive integers. So just as a really kind of overly drawn figure, I tried to sketch out the first few to some bad scale first allowed orbits. So basically, if the electron is in this lowest state, it can't fall any lower. That's the ground state, and it's at 1 Bohr radius. The electron there, or the energy of the system, is minus 13.606 electron volts. In other words, you would have to add 13.606 electron volts to free this electron or more, right? The next allowed orbit is 4 times bigger, right? 4 times the radius. And I take this minus 13.606 electron volts divided by 4, right? Divide by 2 squared. This is the n equals 1. This is the n equals 2. So this electron, or the atom when it's in this configuration, has a system energy of minus 3.402 electron volts. So if the electron were to be in the n equals 2 state, and it were to fall back down to the n equals 1 state, it would have to give off a photon of energy equal to, well, coming back to our earlier statement, it would have to give off a photon of energy equal to the earlier state minus the later state. So in this case, a photon of energy minus 3.402 electron volts minus 13.606 electron volts, or sorry, plus 13.606 electron volts. That would equal HF, right? Hopefully that's all right. The n equals 3 case is all the way up here, right? And you can see why I didn't draw the n equals 4 state. I couldn't even fit the n equals 3 state entirely on our video wall. So this is our Bohr atom, and let me give proper attribution. This came from this source. I did make some slight changes to it. I added kind of these upper bars and also the text on the side. Obviously, you can see my horrible handwriting. But in our next lecture or two, we'll start to look at the Rydberg constant, and we'll look at the the emission spectrum that comes when the electron is dropping from an elevated state to a lower state. So the Lyman series is when it's dropping from one of these higher states to the n equals 1 state. The Balmer series is when it's dropping from a higher state down to the n equals 2 state. Paschen series is when it's dropping from an elevated state down to the n equals 3 state. The Brackett series is when it's dropping from an elevated state down to the n equals 4 state. These are kind of rough approximations for the first I think seven or so. One, two, three, four, five, six, seven. Seven energy levels of allowed orbits. Um, but that is our Bohr atom. And again, remember that we're going to have to clean this up a little because while it works reasonably well if you squint um, at describing what's going on in the hydrogen atom, it starts to fail uh, once you look at uh, more complex atoms. And in fact, even if you really closely examine the hydrogen atom, you can start to see uh, some causes for concern. So we'll get to that in due time, though. For now, we're gonna start with this Bohr model. So coming up soon, uh, Louis de Broglie, the Rydberg constant, where we'll examine this stuff, um, and and lots of other really cool stuff. So thank you for stopping by. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your weekend, but not so much that I don't see you on Monday.